Welcome back to the Cosmic Classroom. So I had some questions this week about the relationship between Newton's version of Kepler's third law and Kepler's third law. So the book shows you that Kepler's third law is p squared equals a cubed. The period of orbit around the sun depends on the average distance from the planet to the sun. Newton's version looks similar, but for some it may not be similar enough. So Newton's version showed that p squared over 2 pi squared equals a cubed over gm plus big M plus little m. Those two relationships are exactly the same in the case of a planet orbiting the sun. In the case of a planet orbiting the sun, big M, the mass of the big object, and little m are pretty much equivalent to big M, all right? And if you plug in all the constants here, g and 2 pi, and if you use a in the SI with meters per second, a in meters, and if you use the period in seconds, and if you do all the math, you end up with p squared equals a cubed if you do the unit transformation. They are the same thing, but you're still not convinced, and you still don't understand why is it that there are two versions. Kepler's look much better. The problem is that Kepler's is only useful for the solar system. It's only useful when there are two bodies interacting and one of them is much more massive than the other, so that we can discard the mass of the second one. However, in many cases, the bodies may have similar masses, may even have equal masses, and the problem becomes more complex. Also, Kepler, as I mentioned in a previous video, derived this equation empirically. He just observed it to be an equation, while Newton really derived it from physical principles, and that's what I'm going to show you how to do. So Newton's version becomes important when we have two bodies, and we can't ignore the mass of either one of them. We can't say that, oh, that's very small. So here I have a big body that I'll call big M, and I have a little one that I'll call little m. And they are at a certain distance apart that I'll creatively call d. All right. The center of mass of the system, the place that this objects will orbit, it's neither the center of big M nor the center of little m. It's somewhere in between. And it's called the center of mass. That's where they will orbit. So this object here, big M, will orbit like this. All right? Oops, that should be a circle. While the object little m will orbit around the center in a circle here. So they orbit this way. The distance from the center of big M to the center of mass, I will call d underscore big M, the distance from M to the center of mass. The distance from the center of mass to the little mass, I'll creatively call d little m. Now, the position of the center of mass depends on the mass of these two bodies in such a way that dm, the distance from the little body to the center of mass, is equal the big distance, the total distance from one center to the other, that multiplies m divided by little m plus big M. And you could do, an analogous relationship. You can also say that the distance from big M to little m is also equal d. And now here we would have little m, and again, m plus big M. So things are getting more complicated. The reason the objects are orbiting the center of mass is because they are attracted to each other gravitationally. So the little m is attracted to big M with a certain force F, just as much as the big M is attracted to the little m with the same force, right, due to gravity. So the force of attraction depends on the constant of gravitational constant, the product of the mass of the two bodies, and the distance between their centers square. Now, each one of these objects is orbiting in a circular orbit in this case. So I'll pick one and look at what's happening with that one. So let me pick little m. So little m is being attracted by big M with this force, and this force is then acting as a centripetal force. So this force is also a centripetal force that depends on the mass of little m, on the velocity square little m, and the distance. But now it's not the distance from big M to little m. Instead, it's from the distance from little m to the center of mass, which is dm. That's it, right? So the two forces, this force is the force that is creating a centripetal circular motion. So those forces are equal. So now I can say that Gmm over d square equals mv square over dm. This m goes away with that m. And now let's remember the definition of velocity. So the definition of velocity right here is the distance traveled, in this case, 2 pi dm divided by the time that it takes to go around, which is the period, p. So I'll go back here, and I'll substitute v for 2 pi dm over p. So gm over d square equals 2 pi dm, all of this square, over dm p square. Gm d square equals 2 pi square, that multiplies dm, divided by p square. I hope you follow that much. Now, we are almost there. We need to remember that dm is d that multiplies big M over little m plus big M. So now, all we need to do is substitute this dm right there, and things will cancel out. So let's do it. Gm over d square equals 2 pi square that multiplies d big M little m plus big M right there. I just brought this instead of dm over p square. All right. So we rearrange this. We bring the p squared this way, the d squared that way. With this will become a d cube. And you already start to see that you have the p square, you have the d cube. This m will go away with that m. And look, you suddenly got Newton's version of Kepler's third law. G that multiplies m plus big M over d cube, because this one went there, equals 2 pi square over p cube. Cross multiply, and you have what you really want. P square over 2 pi, all of it square, equals d cube that multiplies g little m plus m. And remember that d is the average distance. It's the distance between the two centers. So this is your a that you saw it as an a. Pretty easy. Boring, but easy. This is it. I hope it helped those of you that wanted to see what's the relationship between Newton's version of Kepler's law and Kepler's law.